We're going to start our next session, and the first speaker, I'm very pleased to introduce Quoc Le, who is a researcher at Google Brain, and who you may not know, was named in 2014 one of the top innovators under 35 by MIT Tech Review.
Thank you for the introduction. My name is Quoc Le. I'm a member of the Google Brain team in Mountain View. In this talk, I'm going to tell you a little bit about my recent work with some of my colleagues in using reinforcement learning to design neural network architectures. So one of the most important results in the last few years in deep learning, in my opinion, it is the use of convolutional neural networks for images. And this started in 2012, but maybe a little bit earlier too, and especially when they use it for ImageNet competition. And started in 2012 with AlexNet, and all the way to now, we have better and better neural networks. And if you see the figure on the left, you see that the progress of the top one accuracy of human design neural networks over time. And this progress has been always about how to design better neural networks and better training schemes for convolutional neural networks. And you can go from 55% to more than 80% with just better architectures. And if you look closely into Inception V4, which is the network that got 80%, you will see the network can become quite complex. The Inception V4 is composed of a bunch of modules called the Inception modules. And in the Inception module, we see a bunch of average pooling, convolution, and etc. So it can be quite complex. So when I thought about this, I said, if this is the future of computer vision, there would be no chance that I can contribute to this research area because it's so complex. It takes so many years of human expertise to design good architecture like this. We just recently started using more automated method to design neural architectures. And the key idea is that, the key observation is that even though neural architectures can be complex, they can be thought of as programs or like configuration strings. So let's suppose that I have this configuration string called filter width of 5, filter height of 3, and number of filters of 24. I can kind of reconstruct like one layer in the neural net. So the idea is to use an RNN to write down this configuration string. And then when you write down that configuration string, you need a parser to parse that configuration string to construct a neural network. And then you take that configuration neural network and train it to the end. And then validate it on a validation set. And then you get a reward signal. And then you use the reward signal to feedback into the controller so that the controller can improve over time. So the picture of the method will look like this. So we have two systems. One is a controller which proposes machine learning models. And machine learning model will be trained and then evaluated. Some of them will be good and some of them will be very bad. And the good ones will give positive feedback to the controller. And the bad one will give negative feedback to the controller so that over time the controller will sample better and better architectures. So in our framework, the controller, again, is like a recurrent neural network. And in particular, we use the long short-term memory network. The way it works is following. So we divide the network into a bunch of layers. So we have layer n-1, layer n, and then layer n+1. And in every layer, you have some particular configuration that the neural net has to specify. For example, it has to specify the filter height, filter width, stripe height, stripe width, and etc. And then the way we train it is basically using reinforce or other policy gradient methods. And first of all, we have the reward is basically the accuracy of the architecture on the held out validation set. And then the parameter of the controller will be optimized using reinforce. And then we can use reinforce to expand the rule and compute the gradient and train the controller. And so the first experiment we conducted was on optimizing convolutional nets for CFAR10. And we have to predict the filter width, filter height, strike width, strike height, and number of filters per layer. For example, filter height, we can select the soft max, can select between 1, 3, 5, 7. And then filter width, the soft max can select between 1, 3, 5, 7. And strike height, strike width, and etc. For example, if the controller for this particular layer write down the string 3, 7, 1, 2, and 36, what that means is the filter height is 3, and filter width is 7, strike height is 1, and strike width is 2, and the number of filters is 36. That's basically what the controller should write. And then it will concatenate these strings for a longer network so that you end up with a bigger neural network. We conducted a massive experiment on this. So we used 800 GPUs concurrently at one time. And each try network was trained like 50 epochs. And we ran, for the total number of models that we trained was 12,000 try models. And in our system, we have, because we run 800 GPUs concurrently, we break it down into multiple replica, and then the replica will communicate to a parameter server for the controller so that the controller can asynchronously update the parameter so that it can sample better architectures over time. When we first applied this to CFAR10, we ended up with accuracy of 3.65 accuracy, error rate on the data set, and this is basically on par or slightly better than most of the architectures that human invented. And the architecture that the network, the controller basically end up predicting was this kind of network architecture. So I didn't talk too much about the skip connection, but in our controller, you can also have a node to predict what layer before that it can connect the input to. So it can choose not to connect to any input or any layer before, or it could predict one layer. And the controller basically selects many skip connections. We also ran a control experiment where we actually manually connect all layers to all layers, all the layers, and the results are actually less good compared to this model. So the controller actually truly optimized for skip connection and size of filters and so on. One thing that I really very interested in is not only doing on CFAR, but also on imagenet. And imagenet is, because imagenet is considered to be one of the holy grail in computer vision, I would say. And when we did the back of envelope calculation, when we tried the method on imagenet, we found out that it's too expensive. It would take months to get the result. And so we came up with a different scheme to reduce the cost. So instead of running neural architecture search to find the configuration for the entire neural network, we find a layer. And then once we have the layer, we can actually replicate it many times on a bigger data set. So here's the way it works. So on the left, you see an architecture that we manually constructed for CFAR10. And in this network, we have two kinds of cells, normal cell and reduction cell. So normal cell is like a normal layer, and reduction cell is like a pooling layer. And then we want to run this architecture search on CIFAR10 dataset. And once we found a good cell, a good normal cell and reduction cell on CIFAR10, we will replicate it many times on ImageNet. Basically, the number of N here going to get increased, and we're going to end up with a bigger neural network, and then we are going to execute it on ImageNet. So that way, we don't have to spend a lot of time inventing architectures directly on ImageNet. When we ran this method on CIFAR10, we discover the following two cells. So the first cell is the normal cell that take HI minus 1 and HI, and basically have a bunch of combination method to arrive as HI plus 1. So you can think of this as like an inception cell, but it's a little bit more complicated. And it's something that I would not be able to figure it out myself. And then another cell this is basically the pooling layer. The pooling layer is basically taking HI minus 1 and HI, and then also perform a bunch of combinations to give rise to HI plus 1. So these two cells are being searched by neural architecture search. And once we're done with that, we're going to stack these cells many times. So you construct a much deeper neural network on ImageNet and train it to the end with, for the entire week. Now, one nice thing about this is that we can decide how big the network on ImageNet we can use. We can stack up, for example, if n equal to 3, we have a very small ImageNet model. And if n equal to 100, you end up with a huge deep model. And that's a flexibility that we can play with. And in summary, when we applied it to CIFAR10, the best network when n equals to 7, this is n equal to 7, using the cutout method, we achieved 2.4% error rate on CIFAR10. And I think this is the best accuracy published up to date. I think there must be some other equivalent accuracy somewhere on some other paper, but they aren't published. And this is probably the latest best so far. Again, when we apply the layer on ImageNet, we can play around with how many times we can stack up the neural network. So for example, if we stack up n equal to 4, you have a very small neural network. And on this axis, on the x-axis, I plot the size of the model in terms of number of operations. So smaller is better. And on the y-axis, I plot the top 1 accuracy, so higher is better. So the best is trying to go all the way to the top left corner of this figure. And as you can see, the network that we found actually better than the skyline, the models that invented by human experts. And including like the SENet, which is basically the best model people found so far. And I think that this is, in terms of accuracy, we're on par, but in terms of size, we're a lot smaller. And similarly, in terms of number of parameters, we're also a lot smaller than the state-of-the-art neural networks that humans found. We also transfer the architectures that we found to the dataset called the Quoc dataset. This is another holy grail dataset in computer vision for object detection. At the time when we applied it, the state-of-the-art is around 39%, using a complicated loss function, and we didn't use it, but the NASNet model that we found was able to achieve 4% better than the state-of-the-art. And 4% better in mean average precision is a huge improvement in accuracy of this model. We also open source the imagenet model, so you can actually download the model and use the pre-trained weights for your problem and replicate some of the result in the paper. And yeah, I can stop there and take questions.
Thank you. Amazing work. I was wondering how can we further reduce the search space, because 800 GPUs is a bit too much. Do you have any thoughts on the future work? How can we further take it down so that we don't all have to use 800 GPUs?
Okay, so I think there have been active research on how on trying to reduce the computational complexity of this of this approach, and I've seen Frank Hutter, like the previous speaker, he was talking about using learning curve prediction. That's one area that very promising, because if you predict what model is doing badly, you can kill it off very quickly. I think Kevin Murphy and friends are looking into some way to do progressive architecture search. So basically, instead of doing massive architecture search right away, you kind of do curriculum training. I think this is also, Barrett is also a co-author of this paper, and I think that can be quite promising. The other idea that a lot of people have been around and is the idea of using multitask. If you have a lot of data sets, right? As humans, we don't ever want to start from scratch. Every time we have a new problem, we basically use some knowledge in previous task. And I think Risto kind of talked about it in early talk. So some combination of those ideas that can actually get you further reduce computational complexity of this approach. Yeah.
Thank you very much for your talk. I have a question. As you know that over here in NIPS, again, we have one symposium focusing on interpretability. Mm-hmm. This kind of approach, for example, as you shown that we can reduce 1% of the test error, mm-hmm. But as you shown the example of cells, the normal cell and another cell, yeah. We could not interpret them. So what is your take on that? I mean, in your opinion, although we can reduce the test error, but it's quite hard to interpret such kind of models. So which direction would you like to, take this forward? Okay,
so maybe we can have an objective, another objective function in the reward function for interpretability. Okay. And maybe the best way to do this is connect it to the NIPS system, so that every time you come up with a new model, you can submit a paper to NIPS. Actually, in reality, we've been thinking about this problem a lot. We don't have good answers. I think they are as complex as any other deep learning systems, unfortunately, but it's an area that we've been spending time thinking about too. So one way to do it is to regularize the grammar, so to make sure that the grammar is something that, for example, ResNet is an idea that people like a lot. It's because, not only because it works well, but it has some regular structure in the grammar. So maybe we can enforce some grammar. Yeah.
Thank you. Thanks.
Yeah.
Thank you very much for amazing research. Unfortunately, not all of us can repeat your experiments due to computational limitations. My question is, how you deal with other hyperparameters that are not handled by the recurrent neural network? So you have to predict them, layer configuration, but what do you do with learning rate, batch sizes?
Okay, so the question is, how do we handle the hyperparameters in the system? So it turns out that it's quite easy to make this whole system not work. The idea here is to make that system work. And one thing that a few things that we do, and we actually wrote it in the paper too, is that number one is that we don't predict the learning rate. So the learning rate, if you were to allow the controller to predict the learning rate, it would predict the smallest learning rate possible. It will predict the smallest learning rate possible so that if you train it in a short time, the smallest learning rate will actually win. We also make sure that all the models in the system actually have very similar number of parameters, so that otherwise the reward function will prefer the networks that is the smallest because it's going to be trained faster. So those things that we aim for. So the other thing that we did was we copied some of the best, the state-of-the-art training recipes in ImageNet or CIFAR-10. So for example, data augmentation, we copy like the white ResNet recipe. We have this cosine learning rate by Frank and colleagues. So we basically like copy a bunch of recipes that exist in. We didn't do anything fancy there. Presumably, if you want to like take the controller and predict those hyperparameters, it's possible too. But the point that I'm trying to make is accept existing hyperparameters and then just invent new architectures. Yeah.
Okay, yeah. So yeah, my apologies that we're kind of running over time, so sorry about that. Hopefully we can catch you after.